Hello everyone, welcome to this first NewSkin Info Day organized by the European Cluster of Ceramics. So my name is Dylan Juglar. I'm pleased to welcome you for this first webinar organized by the EUCER. So today we will see how the NewSkin project is organized, and we will have different speakers, RTDs who will present their technologies and their facilities. Just to start, one slide for the organization of the webinar and some input concerning the application we are using. So go to webinar. So first of all, I will ask you to raise your hand if you have any questions or comments regarding the presentations, and then once you are allowed to speak, we will let you ask your questions or make your comments. Normally, everyone should be muted, but if it's not the case, please keep your microphone off, please. For asking questions or make comments, you have different tools to use. The first one is the chat section. So we will read the comments and the questions, if any, and then you can also use the questions box. And once there is a question, I will read them and let the speaker answer. And then for the speaker, of course, please use the full screen mode, while you are presenting. And to finish, if you have any issue or problem regarding the connection, or if you have a problem for the audio or whatever, please reach my colleagues, so either Sophie Comte or Alexandra Baudouet, who will help you during the webinar. So here is the agenda of the day. So this is the introduction, of course. Then we had a last-minute issue. Unfortunately, Carlos Del Castillo was supposed to present the NewSkin project, but he had an issue. So he will not be here for the presentation, for the webinar. So I will do my best to do the presentation instead. And then we will start with the presentation from the RTDs. First of all, Thomas Pupa from Uppsala University will talk about the high PIMS method. Then Charlotte Gallois from Carbon Waters will talk about the use of graphene as anti-corrosion purpose. And to finish the first part of this webinar, Santiago Dominguez from Tecnalia will talk about technologies for the improvement of surface properties in dynamic environments. Then we will have a break. So it's supposed to last 20 minutes, but according to the questions and answer, maybe we will make it shorter. And then for the second part of this webinar, Francisco Gontal from MN will introduce laser texturing and additive manufacturing technologies. Then Ronan Batkan from the University of Dublin will also talk about laser processes. And then we will finish this webinar with Roman from Alpha RLH, who will introduce the platform that we are developing and that we'll use for the NewSkin project. You will also be able at the end of this webinar to sign on this platform. And also we will talk about the open calls that will be launched soon, hopefully at the end of 2021. And of course, we will finish by a question and answer section before the end of this webinar. So let's start with the presentation of the NewSkin project. So as I said, Carlos Del Castillo is not here. Unfortunately, he had a last-minute issue. So I will do the presentation instead. And let's start. Enjoy the webinar, and please don't be shy. Ask questions if you have any. Sorry, I have a problem to share my screen. Okay, here we go. Sorry. So let's start for the presentation of the NewSkin project. So first of all, what is NewSkin? So NewSkin was born in 2018 during a ECCS meeting. So meeting identified, first of all, the limitation of current standards to demonstrate the durability of components, surface treatments, and replicate the real operation conditions. And the second point was the limitations of current nanosurfaces technologies, such as low productivity, difficulties to work on heat-sensible surfaces. So according to these points, the ECCS decided to extend the action scope and the consortium composition to ceramics, laser, water treatment, and the industry in general. So what is NewSkin? It's an innovation ecosystem that has been built to accelerate the industrial uptake of advanced nanotechnologies. Among others, we will, for example, find the low productivity of manufacturing process, the difficulties to develop mass production processes, the temperature limitations, nanosecurity and safety issues, and the access to funding and investors. So NewSkin is part of the European project Age 2020. It will last 48 months. It was funded in November 2019 with 15.6 million euros of budget, and it started in April 2020. So as I say, it will last 4 years, so it will end at on April 2024. So one of the main important points concerning NewSkin is the following. So it aims to provide the innovative ecosystem with the necessary technology, resources, and services to uptake a series of game-changing, efficient, and cost-effective innovative processes to manufacture nano-enabled industrial and consumer products and the testing capabilities associated. So we call it NoITB, so an open innovation testbed. And the second important point to keep in mind is that the entities established in at least 3 member states and associated countries will offer access to physical facilities, capabilities, and services that are required for the development, testing, and upscaling of nanotechnology and advanced material in industrial environment. And the principle of this OITB is to go from a TRL 4, which is a validation in lab, to a TRL 7, which is a prototype in industrial environment. So here you can see all the entities that are part of the NewSkin project. So in total, we are 35 entities, among which you can find technology center, industrials as well, but not only. You will find also competitiveness clusters, and all these entities will work during these 4 years to reach the target of the nano-enabled technologies and improved surfaces. Concerning the fields now that NewSkin project is targeting, so there are several, as you can see on this slide. The first one is the steel construction, but there are also the ceramics industry. Water treatments is also an important topic. And you will also find transport, renewable energy, medical device, and photonics applications. And concerning the application, so the first one will be to develop some materials and surfaces for antimicrobial laser textured, especially for aluminum and steel foils, for pharmaceutical and food packaging. Then we will also develop some aesthetical and functional coatings for luxury sector, especially for the ceramic sector, and also some textured and coated propellers and nozzles for low friction, anti-fouling, and improved hydrodynamics. Concerning the timetable, so you can see here the overall timetable. So today we are in the middle of the second year. And as I said at the beginning of this webinar, we will have at the end of 2021 an important step, because we will start the first open call that Ronan will present you at the end of the webinar. Concerning the pilot plants that we are testing right now, we are targeting 10 upscaling plants across Europe for industrial production. Among these 10 plants, we have 2 continuous chemical vapor deposition lines, 3 laser texturing lines, 2 mechanical transfer of textures by texturing during molding and work-to-roll process, and then the last one, which is 1 pilot plant for the safe, automatized and controlled application of nano-enhanced coatings. I will not present the example because we will see some of them during this webinar. So concerning the testing facilities, so NewSkin Open Innovation Testbed will allow to demonstrate improved performance of nano-enabled coatings and membranes versus the standard counterparts replicating harsh, aggressive, and stringent conditions currently non-addressed by available standards. In total, we have 9 test sites across Europe, 5 for the testing of coatings and components under combined either stresses and aggressive industrial or environments, or harsh environmental condition and extreme pressure and temperature condition over 25 years accelerated exposure. So this is just to replicate what we can find in the environment. And we have also 4 facilities for the testing of coating and components in operational environment. I will not present in detail the testing facilities again. Concerning the case studies, so we will have 4 case studies to validate 59 nano-enabled products. First of all, it's gonna be to validate the technologies designed to help attracting end users to the OITB across the open calls. We will also target to demonstrate the unique selling point of the testing and upscaling technologies facilities integrated in the OITB. And then we will also demonstrate the reliability and potential of the route to market and commercialization across different technologies and topics. So first, the nano coatings for components protection under combined stresses in harsh environment and aggressive industrial atmospheres. The second point is nano-enabled membranes for water treatment applications. The third one is the batch processes for the production of nano-enabled coatings and surfaces. And the fourth one is the mass production processes for the manufacturing of nano-enabled surfaces and membranes. Concerning the open calls, just briefly, because again, Romero from Alpha LH will talk more into details about these open calls, but there will be 4 open calls with 25 service provision per call. And among these calls, we will try to define nano-formulated coating on steel and durability assessment and different aspects concerning the antimicrobial prothesis, anti-ice wind blade, for example, and texture molded components. I will not present this one. And concerning the impact, so we did a quick study concerning the economic impact and the benefits. So concerning the global challenge, about 29% of the energy consumed is due to transport. And technologies that we will try to develop within the NewSkin project, we will be able to save approximately 9.13 billion of euros per year, which is a huge amount of money saved. Concerning the corrosion, so approximately there are 2.24 trillion of euros spent in due to corrosion, sorry. And if we manage to improve the lifetime of some components by reaching 25 years of surface protection, for example, for the steel industry, we will be able to save, for example, 20 billion of euros per year. For the medical part, like orthopedic or body implants, we will manage to save 400 million of euros per year. And finally, concerning the fuel consumption, there are 50% that is due to thermal energy losses. And with the technologies developed in the NewSkin project, we will be able to save 1.33 billion of euros by reducing the energy losses and also reducing the gas emissions. So for the future, we aim to make NewSkin as sustainable as possible by creating a non-profit association in order to, after the 4 years of the project, be able to use the technologies, to still use the technologies developed during the project, and to remain sustainable. So that's all for the presentation of NewSkin. Is there any questions or? So if there's no question, we will follow the webinar with Thomas Kubart from the University of Uppsala. So Thomas, it's up to you now.
Yes. Hello, everybody. Thank you, Dylan, for the introduction. I will first start sharing my screen, and hopefully everybody can see my screen now. Is that the case, Dylan?
Yes, we can see it, Thomas.
Excellent. And then when it comes to the time, I promise to talk for 15 minutes, but maybe I get 5 minutes extra or something. Anyway, I will try to make it not too long, so we have time for questions and discussion. But briefly, I think I should first introduce myself. So Thomas Kubart is my name, and I am from the Uppsala University in Sweden. And I'm going to talk about surface engineering, or a specific deposition technique for synthesis of surface coatings and thin films. I was actually considering to ask you now about your expectations, but then I realized it's probably complicated, and so I will simply assume that in the audience there are some people who are experts on techniques like Magneton Sputtering, but there are also some people who are interested in surface engineering and would like to learn more about the different options that are available. So I will try to cover mostly the basics, explain what we are after and what we can do. And then hopefully if you have questions, I can answer them at the end of this presentation, or you can come back via email. And I am going to talk about a technique that's called high power impulse magneton sputtering. And I was thinking about the outline that I should explain what this is about, how it can be used, and so on. But then I realized it's important also to put this in a broader context. So I can promise that I will mention at least some examples of applications, what type of surfaces we can prepare and what type of materials we work with. But I thought the best is if I start like this. Okay, we are going to look at some selected examples, but first of all, I will repeat once again what is the NewSkin. And the idea behind this project is really to bring together a number of partners, because surface engineering, or what's called here advanced surface nanotechnology, that's a very important field. But the most important is that such techniques and materials, they are really important for a large number of applications. So what we are aiming for in the NewSkin context is really to cover the whole chain from development of a new surface to its application on a large area. And that might be the most unique possibility in this consortium, that we are actually thinking about the scaling up. Roughly speaking, so here in Uppsala we work often on a lab scale. So this is one of our deposition tools, and we can develop new materials, we can deposit them on surfaces and test them. But the NewSkin, here we are going to make one step further. So specifically here in Uppsala, we are addressing roll-to-roll deposition of thin films on foils. But there are also other partners in the NewSkin consortium, and in this context, it's important to mention Fraunhofer Institute that can grow thin films on metal strips and sheets. And there will be also a presentation from Tecnalia today, who work on a similar technique, but they are focusing on components and complex pieces. And my point today is, so I'm going to talk about a technique to grow thin films or to coat surfaces. And this technique can really be scaled up So if we develop a new surface that works in the lab, in frame of this project, it is possible to use it on real components. And we will find a way how to do this within the consortium. And since we are also in contact with partners doing testing, then we have a chance to do a sort of complete project, everything from the material synthesis to testing. So I promised to talk a bit about our technique, and I am assuming that at least many in the audience have heard about magnetron sputtering, because that's one of the techniques that's used a lot to treat surfaces. So essentially, the idea is that when we have different components, we would like to have surfaces with specific properties. Very often it is not possible to combine or to use the same material for the bulk and surface, and this is where different thin films and coatings come into the game, because we can coat a surface with a layer of material that might be very hard. It may have interesting optical properties. It can be self-cleaning or whatever you can think about. And I've listed some examples like hard and wear resistant coatings, low friction coatings, corrosion protection, and so on. The number of applications is enormous, so I will not really talk about specific applications. I will just hint towards the different possibilities. And magnetron sputtering is one of the very commonly used techniques. It's an example of physical vapor deposition, and it's really powerful because it works well both on a small scale in the lab, but one of the examples that I like is that, for instance, glass panes for architectural glazing, they are coated by magnetron sputtering too. So what you can see here is an inline coating line for glass panes that are something like 6 × 3 meters, and it's the same technique that we use in our labs. So that's one of the important features and benefits of magnetron sputtering. Another is that there is a large number of materials that can be deposited by sputtering. So again, it's a very flexible technique. But those of you who use sputtering, you might have seen a typical cross-section. So what I'm showing here is we have a substrate, and here we have the coating or a thin film on the surface. And of course, when we do this, the surfaces look nice and shiny, but if we zoom in, look at how the coating looks like in an electron microscope, you would typically see such columns. They may not be bad, but there are times when we would like to have a very dense material, if possible, without any voids and defects. For instance, in corrosion protection, the boundaries between these columns or grains, they can present weak spots, so then there might be preferential corrosion at the grain boundaries. And these are moments when the classical sputtering that is, as I mentioned, widely and frequently used, may not be enough. And this is what I'm going to talk about today, because the technique I mentioned in the title, high power impulse magnetron sputtering, that's actually a further development of the classical magnetron sputtering. From the hardware side, it used the same deposition system, the same magnetron source, but we do some tricks, and that way we can actually ionize the material that should be deposited. So instead of neutral atoms, we would be depositing ions. And I will talk for a minute or so about how does high power impulse magnetron sputtering or high PIMS, how does it work? But I show one example here. So this is titanium oxide. And again, when we zoom in and look at this film that's about 200 nanometers in thickness, we can see that we can control the morphology. So when we use more ion assistance, we can make the coating much denser. And when you look at the surface, we can also make the surface smoother. So when we do things right, we can make a very dense coating that in the cross-section does not show any noticeable features, and we can also make the surface very smooth. And this may be useful in various applications. This is today more about what we can do, but I will still spend 2 slides on explaining how does it work. So at least for those who are familiar with Magneton sputtering, we use a sputtering target, and then in a plasma discharge we can eject atoms from the sputtering target surface, and we can let these atoms condense on a surface that should be coated. That's a technique that many of you have seen, I'm sure. It works well. As I said, it's used for a number of materials, and it's also interesting because it can be used at low temperatures, so we can coat even sensitive surfaces. What we do in high PIMS is we use the same hardware, but the discharge, instead of running a continuous discharge all the time, we would apply the electric power in short pulses, and that's what this sketch is trying to show. So the average power in the discharge measured over time is about the same as in a normal sputtering, so we can cool the sputtering target, and then the process is okay. But in these pulses, the plasma density is much higher than in the continuous magnetron sputtering process. So not only we would sputter out atoms from the sputtering target surface, but we can also ionize them. And this is what makes the difference. So now large fraction of the material that's being deposited, those are actually ions. And in general, high PIMS has been around for maybe 15 or 20 years now. And it has been shown that in many cases it gives materials with very interesting properties. And as I said, I will mention a couple of examples. Since I am not sure about your background, I thought I would take maybe 2 or 3 different cases. When I see the time, I will do this very briefly. So I will start with carbon, because diamond-like carbon or carbon-based coatings, they are very widely used. And I don't have time to go through all these slides in detail. So I will just say that we've done some work on amorphous carbon deposited by high PIMS, and we could reduce the wear rate of these coatings by about an order of magnitude. Because we could make the carbon coatings very dense. They were not as hard as the typical tetrahedral amorphous carbon, but the wear rate was comparable as the sort of state-of-the-art hard coatings. So carbon coatings, they are useful for low friction and wear resistant surfaces. We have also looked at different type of friction surfaces, and you don't really talk about high friction surfaces. So the question here was rather, how can we make friction between 2 surfaces stable? And this was an application where alumina is used for components that are in contact. And it turned out that one of the issues is that although alumina is a very good hard material and everything, the surface is sensitive to air humidity. So depending on the environment, the friction between these 2 surfaces can vary a lot. And it's especially difficult if alumina parts should be used in vacuum, because what can happen then is that the two surfaces are really in contact. There is no adsorbed layer on these surfaces that would separate the two components, and that these surfaces can in a way weld or stick together, and this limits terribly the lifetime of the whole system. So we looked at the use of chromium nitride on alumina, well, actually at alumina interface on one surface of alumina in contact with another alumina component. And we did some work on this. We found that chromium nitride works fairly well, but of course important is to make coatings with good adhesion, and in our case that required quite a bit of stress engineering. So here you can see an example of fairly bad performing chrome nitride due to intrinsic stresses, and then we could make or improve this coating by using high PIMs or ion assistance implemented in high PIMs. I cannot really talk about the specific application, but yeah, the important part was that now by replacing one surface with chromium nitride, the lifetime was increased quite a bit in this specific application. And maybe last brief example, metallization of surfaces. That's an interesting topic that's studied, for instance, or used in electronics, for instance. And nowadays there are applications or cases when the traditional materials don't perform as required anymore. So we did work with cobalt for metallization of electronic components. And the challenge and the exciting stuff happens when this metal film or metal layer is very thin. So we looked at cobalt thin films down to below 10 nanometers. And here we could see that again the growth conditions can change a lot the performance of the cobalt layer, specifically the resistivity. So when ions are involved in the deposition process, the conductivity can improve a lot. And there are some other advantages. So here what you can see is that depending on the growth process, the density of the deposited cobalt could go all the way up to the density of bulk cobalt metal. And one can also tune the microstructure of the material. I suspect I am slowly running out of time, so I will probably skip optical coatings, or I just say that optical coatings like titanium oxide, they're also an interesting topic because the refractive index can be controlled or influenced by the growth process or deposition process, and then of course that through the density changes the refractive index. So we could increase the refractive index of titania from about 2.4 to 2.6. And I've already shown that it's also possible to change the microstructure and surface roughness. So to conclude, we have many exciting techniques that work well in the lab. In the NewSkin, hopefully we can make this one step further and look at how these techniques or materials work on a larger scale. And of course, for those of you who work with different applications, you know that it's very difficult to decide or tell if a surface or material is good or bad. It actually needs testing in a specific application. And then you can say, okay, well, this one is better than that one, so this will work better for us. So for instance, what we work on in the NewSkin project now is to scaling up the titanium oxide on PET foils. And that's also very interesting because that requires low deposition temperatures, as the PET is fairly temperature sensitive. And this is where the NewSkin is coming and becoming very important. So let me summarize this very brief presentation. So I at least mentioned high power impulse magnetron sputtering as a possible next step in magnetron sputtering of materials. And I mention here high performance materials because, of course, high PIMS is somewhat more complicated than standard magnetron sputtering. So it makes sense to use it once the traditional deposition process is not providing sufficient performance. This is in principle thanks to the use of ions in the growth or deposition of the materials. And this approach can be used to improve different coating properties, adhesion, increase density, control the stresses, tune the phase composition. And now we have a chance for scaling up and also testing in collaboration with other partners. And with this, I would like to thank you for your attention. And I hope we have time to answer possible questions. So thank you very much.
Thank you, Thomas. Thank you very much. So is there any question for Thomas? Okay, someone raised his hand. Yes. Okay, so we have one hand raised by Daniel Turover.
Hello, can you hear me?
Yes.
Thank you for the interesting presentation. I have one quick question is it possible to deposit locally?
No, no. So in this technique, yeah. Well, it's a vapor, so it would coat the whole surface. So then what you can do is you can mask part of the surface.
Yes. Is that something you can do? Is it something you'd be interested in testing?
Well, it depends on how locally you mean. I mean, how small features you are interested in coating, because in principle it really depends on the scale. I mean, if it's 1 by 1 centimeter, then it's easy to just tape the rest of the surface and protect it. If it's 20 nanometers, then it needs other tricks.
Well, we would be interested in something in tens of microns or below 1 micron. So this is something we'd be interested in investigating, maybe doing some tests together, and discuss that further.
Yeah, then the best could be maybe to drop an email, because if it's micrometer, then this would probably require some kind of lift-off or lithography process to define the structures.
Yep.
But yes,
that's something we're familiar with. So okay, so I'll follow up by email. Thank you.
Yeah. Thank you. Well, I suppose I have taken too much time anyway.
No, Thomas, that's fine. We still have time. Actually, we have some more questions. We have, well, okay, we have several questions from Sandrine GD. I don't know. So the first question is, did you have quantified decreasing friction?
Okay, and this, I mean, it depends so much on the specific contact situation. So I mentioned this diamond-like carbon or amorphous carbon thin films, and there the friction was not really reduced all that much. What was reduced was the wear rate. So there it was more, yeah, lifetime of the surface rather than reducing the friction. And in the chromium nitride case, there the requirement was not to reduce the friction too much, because the application there was towards a static friction. So sorry, I cannot answer, because this depends on the material in question. And yeah, I mean, friction is one of the challenging topics. So
actually, there was a mistake. The question was, have you seen quantifying the decrease of the friction coefficient?
Sorry, as I said, it depends on the specific material. So I don't know if it was the diamond-like carbon or if it was.
It's not precise in the question.
Because
go ahead. On still.
Yeah, no, I mean, in our case, we were more interested in the wear rate. The friction coefficient was similar for these different coatings.
Okay, sounds good. We have two more questions plus one hand raised. So let's have Jenny Join ask her question, probably.
Okay, can you hear me?
Yes.
Yes.
Okay, thank you. Thanks for this presentation. It's just a short question. I'd like to know about, you showed that the roughness could decrease a lot. Do you have some value of how low you can go in terms of roughness?
Not really. And the trouble again is that then it depends on the film thickness and on the material. So we haven't really measured or quantified the surface roughness. What I showed was mostly electron microscopy. So then we see the surface, but we haven't quantified it.
Okay, thanks a lot.
And we have two last questions. We have just 1 minute left. So the first one from Nathalie Caillou is, are the results for high PIMs also true for all materials?
No, I mean, in principle, the idea is true. We can make, I mean, we are providing more energy to the growing surface, but it very much depends on what's the desired property. So, for instance, it looks like for photocatalytic materials, some columnarity, or I mean surface roughness, is actually useful. So maybe I should say like this: it's not a magic button. It's not that if you switch from direct current to high pips process, you get automatically 50% better performance. It needs some fine tuning, but I dare to say that now at least we have some feeling for how things work. So if you have any specific material or application, talk to us please, and maybe we can figure out how to make the high pips work better.
Okay, thank you, Thomas. Sorry, it's already 2:51, so we will stop with Thomas, but we will keep in mind your questions and we will answer them probably at the end of the webinar. And if we don't have time to answer to all of the questions, don't worry, we will send them to our speakers and we will send you the answers after the webinar. So thank you again, Thomas.
Thank you.
Let's go on with so Charlotte Gallois from Carbon Waters.
Hello.
Hello, Charlotte. Go ahead.
Yes. Yep. Is it okay for everybody?
Yeah, that's perfect. Thanks.
Okay. So thank you, Dylan, for your invitation to present our anti-corrosion application during this webinar. So I am Charlotte. I'm account manager for Carbon Waters. And in the NewSkin consortium, we were not asked to work on this application mainly, but on the water purification. But still, we are developing a solution for anti-corrosion application, and that's I will present you today. So, Carbon Waters was created in 2017. We are located in France near Bordeaux, and we are part of different programs and projects. For example, project with Nouvelle-Aquitaine region, with France, or with European project as NewSkin. We received seed funding in 2018 for our launch, and today we are working on the Series A funding to go further in our production process, to increase and to scale up the production process of what we are doing. And we are supporting by that, by Raymond Michel from Firmenich and Patrick Maestro from Solvay. So Carbon Waters designs, develops, and produce ready-to-use multifunctional liquid additive based on graphene. Graphene is a nanomaterial, very efficient, even at very low concentration. And what Carbon Waters does is to make it easy to use by any industrial, any of our clients. These additives are able to boost simultaneously many properties in different matrices, different materials as polymers, composite, coatings, adhesive, but also oils, thermal fluids, or even concrete. Our engineering office work on development with industrial, many development with industrial company by year for many industrial sector. But let's describe a bit what is graphene. Maybe you have already heard of it, but here a little description. Graphene is a material only composed of carbon, and it's very thin. Actually, it's the lightest, the most resistant, and the most impermeable material known today. and it also presents a very nice thermal and electrical conductivity for a non-metallic material. That's why we say that graphene is a multifunctional material. And as a multifunctional material, it could answer many applications in many industrial sectors. So here you can see that graphene can be used for thermal management application, for mechanical reinforcement in composites or polymer, for example, for electrical conductivity in defense or electronic application. It also has lubrification properties. We have worked a lot on anti-corrosion coatings, and I will present you just after. It's also used as to improve barrier properties in materials, for example, for coating packaging. And with the Nouvelle-Aquitaine region, we answer a project about the antimicrobial application for cosmetics or medical application, for example. So here's some example of what we have already achieved with our development with graphene. So we put graphene dispersed in different matrices to improve different properties. So here you have an example on the improvement of mechanical strength of an epoxy resin. So we obtain a significant improvement even at low concentration. It was the same for a thermal application. We put a small quantity of graphene in an additives resin based on epoxy at low concentration, and we get improvement. And also we put graphene in a coating for packaging, paper packaging, and we obtain an improvement in water permeation. But according to the corrosion protection, how does it work? How does graphene act? It's very different as sacrificial or passivation protection. Here we have to see graphene as a 2D material which will act as a physical barrier against water or other corrosive agents. And if you succeed to get your graphene well dispersed in the coating, you will increase the path permeation of the pathway of the permeation path, of the oxidative agent through the coating, and the corrosion will occur later. And this is possible because of, or thanks to, the graphene barrier properties. But when we say graphene, actually, we have to keep in mind that graphene is not an only material, but at least a family of several materials with different properties according to the process of production. According to the process of production, you will more get very thin graphene with few layers, or at the contrary, graphene with many layers, and according all these particularities, you will get different properties. And this has an impact on the application you want to use, for what you want to use it. For example, for the anti-corrosion application, often you will find graphene as powder, and you have to mix it in the dispersion, and you have to be sure that your dispersion stays stable in time. At Carbon Waters, what we are doing is we provide graphene already dispersed in a premix or a pre-dispersed formulation compatible with your paint or your varnish. And we do the same. We actually look after the stability of the dispersion. And this stability is a key point, because if the graphene is not stable in your formulation, in your paint, for example, you will, for the same quantity, you will get agglomerates of graphene, and you will not have the same protection effect because you will lose the network of graphene in the paint, in the coating, and the permeation path of the oxidative agent will not be disturbed by the aggregate, contrary to if you have graphene well dispersed for a very small concentration and the same concentration, you will have a better protection. So stability is really the key for this application. And for that, Carbon Waters used a patented process to produce graphene dispersion from graphite. And the assets of this process are several. The first one is we are sure of the quality of the graphene because it doesn't change when you transform it in powder, because we don't have to transform it in powder. It's already dispersed, so it's easier to disperse it after in another matrices. We do not have to work with nano powder for security and environment things is better. We also do not need other additives or surfactants to get our dispersion stable. And we have shown that our graphene is biodegradable. So thanks to the dispersion we produced, for example, the water graphene dispersion, we have an excellent quality of our graphene because it's reproducible even at nanoscale. It's stable for more than 3 months. It's biocompatible and biodegradable because it's only water and graphene. And from this dispersion, we can develop customized graphene dispersion with different kind of solvent, aqueous solvent, organic solvent, something else. And we can work on paint, varnish, surface treatment, oil, concrete. Yes, it's very large. And for the anti-corrosion application, we have made different tests. So we dispersed graphene in an epoxy-based varnish at very low concentration. Here we are at 25 ppm of graphene in the paint, in the varnish, sorry. And you can see on the right that the graphene varnish show better results after 100 hours inside spray. But this varnish is not representative of an anti-corrosion coating, so we do the same with paint already used for anti-corrosion application in aerospace industries. And here on the above photography, you can see the graphene doped paint after 1,000 years at salt mist. And on the photography, it's not very clear, but that we can see it's better. The result of the protection is better because on the scratch, we can't see with the graphene dop any delamination or bubble of the paint. That is not the case for the reference, where we can see a picture of corrosion and bubble and delamination of the film begins after 1,000 hours. So here we can see that graphene have very significant effect even at very low concentration because it's on here you have I have presented you results where graphene are present at less than 50 ppm. As the graphene is a material very thin and very light, it's compatible with many or all industrial application traditionally used. It's compatible with inject, with spray, with roll-to-roll and many other treatments. And because it's material chemically inert, it's compatible with a wide range of formulation and it's resistant to quite high temperature. So Carbon Waters design and product pre-formulated graphene for the different application we are working on. We do not use additives that can be not not good for the stability or for the formulation where we put the graphene in. The stability is very good. The process we use is reproducible at nanoscale, and we are working on the scale up. We work a lot in collaboration with industrials to be focused on their development and to provide them the answer, the best answer for their constraints, for their needs. And because the main work of carbon motors, instead of producing graphene, is to develop the additives the easiest to use for our clients. And so that way there is nothing to put in place very specific in their process to use it. That's our aim. So I thank you for your attention. I would be pleased to ask your answers if you have, to answer your question, sorry, if you have.
Thank you, Charlotte. Thank you very much. So there is one question in the question box from Nathalie Caillot. So in the case that we are depositing graphene on metal, is it still impermeable?
Yes, there is a different way to use graphene. It's the first way we are developing, or where we are the most mature, is to put graphene in a formulation of coating already known to improve its properties. In that way, you use graphene as an additive, or you can also deposit graphene directly on the substrate by spray or electrodeposition, something like that. And yes, it's still impermeable, but here you have to be assured that your film of graphene is very uniform everywhere on the substrate. And there is another thing we have to be aware is how to say? Sorry, I left my word. There is a problematic of corrosion between carbon and steel, for example, because carbon is more noble metal than steel. So in that case, we are still working on this problematic, because probably graphene deposition is not the best alone to protect steel or metal. Instead of it's ore or platinum, gold or platinum, because they have a very high current. I don't remember the name. Sorry. Yes, they are noble metal. So in that case, it could be okay, but in other metal, it's not the best way for now. We have still work to do.
Okay, thank you, Charlotte. We have a second question by Mohamed Boudifa. Is the deposit compatible with curing processes?
Yes. It depends on the material you put in where you put graphene and the temperature of the cure. As I say, graphene is resistant to high temperature, but it's not very high temperature. It's okay for polymeric or thermoplastic or thermodissociable matrices. But for example, if you want to put it with ceramic and make the sintering, the temperature are too important. We are sure that our graphene stays stable till 400 degrees Celsius degrees. Above, we have to make some tests.
Okay, thank you. We can stop now if there is no more questions for Charlotte. I don't see any. So Charlotte, thank you very much for your presentation.
Thank you.
Let's go on with the next speaker, the last one for this first part. So let's welcome Santiago Dominguez from Tecnalia. Hello. Hello, Santiago. Okay.
Can you see my screen?
Yes, we can see your screen.
Okay, thank you very much, and thank you to give me the opportunity to show you the work that we have done in the NewSkin project. So I'm Santiago Dominguez. I'm working at Tecnalia in Spain in the surface engineering platform. So I'm going to talk about the modification that we have done in our high-pins unit for robust and durable topological and oxidation-resistant coatings. So here's a small index of the presentation with an introduction. I'm going to skip it because it's about high-pins and Magnetron Sputtering. So Thomas has already talked about that. So I'm going to skip it. And okay, I'm going to talk about our facilities descriptions and different coatings that we can apply with our system. So, okay, our Magnetron Sputtering system unit is a Themecon high-pins unit with 6 magnetrons. 4 of them can work in DC or high-pins mode, and the rest of them only in DC mode. The main feature for the modifications of that we have done in the NewSkin project in order to upscale this unit is in the packing chamber. The volume, the position volume of the unit is a cylinder of 400 millimeters of diameter and also 500 millimeters of height. And the turntable that we have in the vacuum chamber is a turntable with a planetary rotation. The standard configuration for this unit is this planetary turntable designed mainly for cutting tools. Here you can see a picture that is the usual configuration for these units. But okay, if you want to coat different pieces, like high volume pieces, you have to do modifications. And also another parts that are sometimes really complicated to coat is some pieces like rings, difficult geometries like the inner track of, for example, of outer ring of ball bearings. So here you have an examples of the modifications, in this case for both the turntable for heavy pieces. Here we have a dummy columns simulating these heavy pieces, because if you have a bigger part, you have to use the whole turntable. This is the biggest part using 2 units of samples. And in the other case, we have also this modification with the turntable. We have six towers with planetary rotation, and with this device we can also spin the rings along its axis. So what we want is improve the homogeneity of the coating inside the rings, in the inner surface of the rings. So currently we are working on that, this part, and in this case we have also obtained a good result in homogeneity, because if you don't have this rotation, you have more thickness in the parts of the in one part compared with others. So with the rotations, we can obtain a very homogeneous coatings in the inner part, in the inner surface of the coating of the rings. Another modifications that we have done is introduce a control of the temperature for the unit, because it's a very important parameter when when you produce coatings with these techniques with magnetron sputtering. So in this case, we have a passive method that by means of metallic thermometers that we have placed on the substrate position. So after the coating process, we can know which is the maximum temperature applied to the process. And also we have introduced a control of the quality of the vacuum, inside the vacuum chamber by means of a device that is an optics from Gencoa. It's an optical spectrometer that gives you an information about the species that are present in the vacuum, and also can give information to another unit that is a speed flow from Gencoa that can controls the flow of the gases in the reactive magnetron sputtering processes in order to have a closed loop control for these processes that sometimes is very complicated to do without this system. In the case of the coatings that we are working on, are 3 different coatings: molybdenum disulfide doped by tungsten carbide, chromium aluminum nitride coatings, and also DLC coatings. In the case of molybdenum disulfide coatings, these coatings doped by tungsten carbide, this sort of coatings show a low friction coefficient under vacuum, cryogenic temperatures, and also resistant to humid environment when they are tested at atmospheric conditions. But which is the origin of these lubricant properties? Okay, it's the microstructure of the compound. These compounds also, for example, not only molybdenum disulfide, for example, other chalcogenides shows the same structure. Is a lamellar structure, so between platelets, here you can see a picture about this structure. Between platelets, you have weak forces, van der Waals forces, that compared with the forces between atoms inside the platelets are very weak. So if you apply shear forces, you can obtain an easy sliding between these platelets. So the result is that you have a very low coefficient of friction. These coatings has been tested in orbit, in our case in orbit, in the International Space Station, at high vacuum, and in different relative humidities in atmospheric conditions. So the result is that also in orbit and in vacuum you have the best results, because there is no water, there is no oxygen, so you have a very low coefficient of friction and very high endurance. And also when you are increasing the presence of oxygen and water vapor, the endurance is reducing and the coefficient of friction is also increasing, but always below 0.2. So it's a very good result. And the origin of this good result is the presence of tungsten carbide that shows that the film has a longer durability under vacuum than pure molybdenum disulfide films. The presence of this dopant gives to the coating a better resistance to the humidity and to the wear. Which are the potential applications? Mainly tribological applications under vacuum or cryogenic environments. The target end users are mechanism manufacturers, mainly low friction devices, and the substrates, metals, alloys, ceramics, and some plastics if the temperature of the critical temperature of the plastic is below or is below 180 Celsius degrees. This process is a low temperature process, so we can apply in high different substrates. In the case of chromium aluminum nitride, incorporation of the aluminum in the chromium nitride coatings shows an increase in the wear resistance and also in the oxidation resistant properties, and also reduce the adhesion for different materials, for example, in different applications. Okay, so the aluminum replaces the chromium atom in the crystal lattice and also forms a solid solution. And these aluminum incorporations produce an increase in the hardness and in the oxidation resistance. For example, we have results in the case of 100% steam atmosphere and also 650 Celsius degrees. And you can see here the uncoated substrate increase in the mass compared with the coated samples. So you can see a very, very different behavior and improvement of these protections. And also in the case of the air, you have an increased protection behavior at 850 Celsius degrees. And regarding the topological properties, compare these coatings with two different synthesized by two different techniques, DC and high pinch mode. What we can see is that in the case of the coefficient of friction, there is no significant differences, but in the case of the wear rate, we can obtain a decrease of this value. So the potential application are oxidation resistant application, wear resistant applications. The target end users are steam turbine components for power generation plants or cutting tools, forming tools, etc. The substrate materials can be metal, alloy, ceramic, and the process is developed at 480 Celsius degrees, but also can be adapted to less temperature. Okay, in the case of DLC coatings and chromium, the DLC is diamond-like carbon. Okay, the carbon can be in two different hybridization modes, sp2 and sp3. With sp2 you can obtain graphite, with sp3 diamond. If you can produce a material with these two different crystals, monocrystals, or amorphous structure, this ratio between sp2 and sp3 defines the properties of the material, the hardness, the lubricant properties, etc. So now we are currently working on this in these coatings with this unit. In order to obtain a good adhesion, we are going to apply a chromium underlayer, and the potential applications are mainly topological applications with different target end users like automotive components for example, the inner of the cylinders or the segment of the pistons, cutting tools, also medical applications, because DLC is a very, very good material for this kind of applications. The substrate materials that we can use are also metals, alloys, and also some plastics, but I have to say that it's very important, the application of an underlayer in order to obtain a very good adhesion, and the temperature that usually develops these coatings are below 150 Celsius degrees. So, okay, That's all. Thank you very much. If you have any question, please ask.
Thank you, Santiago. So for the moment, we don't have question. Oh, one hand raised by Daniel again, to over.
Yes.
Okay.
Hear me?
Yes.
Good. Thank you. I have the following question. How thick need the, for example, the chromium layers be in order to be effective, and how can you control the thickness of those layers?
Okay. Okay. We usually start applying 300 nanometers in order to check by scratch test after depositing the DLC coating, but also you can apply a stack of different underlayer, starting with chromium, changing to chromium nitride, and for example adding tungsten carbide. It's something that now we have to optimize in our system.
I'm sorry, I didn't quite get your answer. My question was really, is how thick do the layers need to be to provide the intercoat? And for example, the chromium for wear and tear application, and how can you control the thickness of the layers?
Okay, the thickness is enough. You can start with 300 nanometers. And also, how you can control this thickness. With a previous deposition process, you can obtain the deposition rate of this material under the condition that you want. So once you have this data, you can adjust the time deposition in order to obtain these 300 nanometers or other thickness.
Okay, thank you.
We have another question by Claudio Ferraro. It's the following. Which is the advantage of these DLC coatings compared to the traditional deposition processes?
Okay. In this case, Magnetron Sputtering technique can give you a different advantages. You have a very good control of the thickness of the coating, and also is very conformal, so it follows very well the substrate. So in some applications it is needed. And also you can control the microstructure of the coating by changing the deposition parameters. For example, the temperature, bias polarization to the substrates, power applied to the targets, etc. And also you can introduce, you can co-sputter different materials. For example, you can introduce, for example, silver in order to obtain another functionality of the coating. For example, antibacterial functionality. It's a technique that it is very, you can do a lot of things with Magnetron sputtering and different materials.
Okay, thank you, Santiago. No more question for Santiago? No, I don't see any. So we can make the break now. Sorry?
You're welcome. No, it's a joke.
Okay, so let's have a break right now. Thank you again, Santiago, for this nice and interesting presentation. So at the beginning was the 20 minutes break, but I think we can reduce it a little bit by 5 or 10 minutes. I would say let's start again at 3:45. So it's a 15-minute break, and we will continue the webinar with Francisco Gontat from Aymen. So see you in 15 minutes. Thank you. Welcome back, everyone. I hope you enjoy your break. We will continue this webinar with Francisco Gontas from MN. So for 20 more minutes, and then we will go on till the end of the webinar. Francisco, it's your turn now. We can't hear you, Francisco. You're muted.
Okay, now it's working.
Yep, perfect.
Sorry for the sorry for the problem. Well, thank you for the presentation. My name is Francisco Gontas, and I work at the MEN. And this afternoon, I will present this work, which is this presentation, which is entitled "Laser Texturing and Additive Manufacturing for Tailored Optical Properties of Surfaces." I guess I could have chosen a shorter title. A little bit long, but I will try to do a short presentation. I work at Advanced Laser Micro Manufacturing Applications Group at MEN, which is a research center at the north of Spain. Our main work is mainly on additive manufacturing and subtractive manufacturing, laser micromachining, drilling, high precision welding and cutting, or surface texturing. And as I said, also on additive manufacturing. Lasers can be used either for the fabrication of textures of surfaces through additive manufacturing, through techniques such as multiphoton polymerization, or they could also be used for the fabrication of this optical surface through subtractive manufacturing, which is an example, for example, of micromachining, drilling, laser drilling, or surface texturing. These three are examples of subtractive manufacturing that could be used for the fabrication of optical surfaces. I will start by describing the two-photon polymerization process, which is the additive manufacturing process that we use at MEN for the fabrication of optical surfaces. The two-photon polymerization is based on a nonlinear effect, where the absorbance of the light emitted from the laser is let's say is only important or considerable in a small area where you have a very high photon energy per volume and time. In the case of radiations, we have a high photon energy, which is the case, for example, of radiation with ultraviolet wavelengths. The absorption of the light is produced along the whole material. So through the whole path of the laser, you will be producing the excitation of the elements, of the atoms, or the molecules inside your liquid or your material. However, in the case of the nonlinear effect, you will be exciting these molecules only in this small volume, as like the small dot, green dot that you can observe here in the green liquid tank, which is called voxels. So if you take advantage of this effect in order to produce the polymerization or the curation effect of the resin, we can change the state of this polymer and make it more soft or more or harden it. This is a very well-known principle which has been used in conventional lithography, which you put a mask, you radiate, just sample your resists with ultraviolet radiation, and you can produce a pattern by choosing the design of the mask that you want to use. By changing the mask, you will produce a different pattern. So by using different masks, you can produce different 3D objects or different kind of patterns. Instead, with two-photon polymerization, what you can do is to select your small volume, your small voxel, and move it, your high-intensity photon beam, and move it along inside the resin, sorry, with the adequate path in order to produce the 3D form what you want to fabricate. One of the best, let's say, points of this technique is the fact that you can produce with complete free design 3D free forms. So this means that you can produce anything that you want inside the resist. You don't need to do successive paths just by moving the voxel inside the resin. You can produce any 3D shape that you want. As you can imagine, the drawback of this technique is the fact that if you have to move this very small voxel inside the resin in order to produce a 3D object, you will need some time in order to produce something which is large. So in order to use this technique that has the excellent advantages producing 3D free form inside the resist, you will have to use it in a way that the fabrication time can be reduced to make it not comparable, but at least competitive for some applications with respect to other techniques, such as I said, conventional lithography or nano-implant lithography, or some other techniques like molding, for example. So one of the main approaches that we have taken as main was the parallelization through the use of parallelization optics of this technique, which is photopolymerization. You can achieve the parallelization of this technique through the use of fixed optics, like, for example, diffractive optical elements, or by using dynamic optics, which, for example, is like the use of spatial light modulator, which are like the small screens that you can find in small projectors, LED projectors. By using this kind of optics, you can change one single beam, one very focused beam, in an array of different spots. Like, for example, this DOE that produces an array of 51 by 51 parallel beams, or like the other DOE, which produces a periodic intensity distribution, which allows you to produce, for example, 1D prisms in the resist, by just scanning this shape, this periodic light intensity, inside the resist. I will show some examples after this first slide, where I explain more or less the technique. That you could also use dynamic optics. The dynamic optics has the advantage that you can produce any pattern that you want. With a DOE, you must have some symmetry, some pattern in order to fabricate something with this parallelization technique, while the use of dynamic optics allows you complete freedom to fabricate in 3D anything that you want. It doesn't need to have some symmetry. You can change your pattern from one shot to the next one, and so by successive changing the pattern, successively changing your pattern, you can produce anything that you want inside the resist, any 3D pattern. There are several strategies to improve the fabrication of this with this parallelization optics. For example, if you go to the simple case, if you want to fabricate something like parallel lines, if you use it with the single beam, you have to go to the first part of the line, you scan it through the resin, then you go to the beginning of the second line, you scan it again, and then to the third one, and so for the number of lines that you want to write in parallel. However, if you have a DOE with 3 parallel arrays, you can scan it and you will be fabricating parallel lines 3 times faster. It's easy to see that if you have n parallel arrays, you can fabricate n times faster. If you want to fabricate a pattern, something which has a certain symmetry pattern inside their own structure, you can either do it by as before by single beam, so you will be scanning the laser beam through your resist and switching on and off the laser in order to produce the pattern that you want to do. Or you could design a DOE with a certain pattern, flash it on an area of the resist, move it to the next area, and then by successive steps of moving and flashing, you can produce the whole pattern in the resist at a much faster rate. So this makes more easy to be more competitive, this technique, with respect to other competitors like I said, lithography or some other kind of techniques, similar techniques. There is another possibility, which is the use of dynamic optics. As I said before, you can just, for example, if you want to replicate something which is like this logo, you can split it in four, for example, in 4 pieces. Go to the first quadrant, flash it with the first shape, go to the second, flash it with the second shape, to the third one, to the fourth one, and so you can, by flashing different images, you can produce an overall image with any shape that you want to plot inside your resist. These are some examples of fabrication, of parallel fabrication with 2-photon polymerization. On the left side, you can observe an SEM image where we have fabricated an array of pyramids, 121 pyramids, by scanning this DOE of 11 by 11 inside the resist and following a path that was the same for the fabrication of one single pyramid. So in one single step, instead of fabricating one single pyramid, we would be able to fabricate 121 pyramids. So we have improved the fabrication time by 2 orders of magnitude. It's easy to see that if we want to fabricate these kind of structures at a larger area, if we use a different DOE with a larger number of beams, we could improve the fabrication time by 3 or 4 orders of magnitude without any problem. If we use, for example, the modulated laser intensity, modulated light intensity DOE that I showed before, we can fabricate on larger areas. For example, this area, this is a polymer sheet which has been fabricated with some diffusing structures on top of it with the resist. By scanning this DOE, the shape of the DOE, perpendicular to the direction of the modulated intensity. So by using the DOEs, we will be able to fabricate this kind of demos in 19 minutes, which is a lot for if we compare it with other techniques. But it's very fast if we compare it, very quick if we compare it with the fabrication of the same structure by using the single beam approach. The interesting thing with this kind of structures is that we can change or select the area where we want to fabricate these structures very easily by just moving the axis and moving to a different area. So we could fabricate this kind of diffusive structures or this kind of pyramid structures in any kind of the substrate that we want to do selectively. Since we only need to, as I said, go to the area of interest, fabricate, and then go to a different area of interest and fabricate again the structure. So this technique is very good to fabricate the design patterns in the areas that we want with a very high accuracy. We can fabricate also diffractive structure. We have that present a colorful effect in different kind of substrates by using this technique. For example, we can fabricate this is an example of the fabrication of the Spanish Royal Mint fabrication of the logo on a glass substrate and then covered with a little bit of a thin film of aluminum in order to improve the reflectivity of the sample. We have produced also the logo on the paper substrate with a very strong colorful effect, and also on PE polymers with the logo of our center. By using a dedicated design on purpose DOE, we were able to fabricate these logos with the size of 18 times 21 square millimeters in 17 minutes instead of the 375 minutes that were required to fabricate it with a single beam approach. The most interesting thing of this approach for the fabrication of these logos or designs or anything that you want to do is that changing the logo or the number of anything that you want to fabricate from the first piece to the second could be changed without any problem within a matter of seconds. You just have to flash a different image. The software that we are using allows us to use a different black and white picture in order to produce the background with a different effect than the letter of the thing that you have in the front in the image. So one of the main advantages, as I said, is that you don't need to fabricate your mask or your mold in order to replicate the same pattern along the whole series or the whole batch that you want to fabricate. You can change the shape or the effect of your batch from the very first sample to the last one by changing only a few parameters in the fabrication process. Let me just show you a quick video of the effect. You can observe how by moving the paper, you can observe the different effects on the fabricated structures. I hope you can see it, because sometimes with the streaming it's not very easy to see this kind of effects. Now let me present now some work on the subtractive manufacturing, in particular in the micromachining, drilling and texturing processes, which is another of the areas which we have some expertise here at IMEN. So we have worked on fabricating diffusive structures. I mean, changing the reflectivity of surfaces by making them dark or less reflected and more reflected. And we have been able to fabricate also this kind of structures on metals for application in plastic substrates. This is an example of here in the metal you have the master, and on the picture on the right you have the replication by injection molding, and here you can observe the effect, like with the texture surface you have a reflection, which is the exact shape of the laser pointer, of a green pointer. But by texturing the surface, we can change the reflectivity of the sample, making that a diffuser of the reflected light. We can do this in a different number of substrates or materials. So this is something that which is in our background, and we could apply on a different number of materials. We have also some experience in the fabrication of self-assembled structure for antibacterial and hydrophobic applications. Like, for example, repetitive structure, periodic density in these periodic surface structures, but with different shapes and sizes. Which has already tested hydrophobic behavior. They have shown some antifouling properties or antibacterial. Antiviral could be possible, but not yet proved. So it's something that should be tested with a specific design, with specific size, and it is something that it's not on the expertise of IMEN yet. But it's something that we will try to develop on the following months or years. We are somehow also experts in direct manufacturing of different pieces, different materials, metals, or some ceramics. We can produce different patterns for different applications. As for example, micro reservoirs for friction reduction, like small pyramid trees. This was a biomedical application, or to make small containers for drug release, like microneedles. We have some experience in the fabrication of microfluidic devices on sapphire, and some other applications in the case of microstructures for the improvement of addition with different materials. We have also some experience in drilling property of different materials with different hole size and a high productivity, more than 300 holes per second. And sorry, I'm going very fast because I think I'm running out of time. And yes, the final remarks, I would like to say that modifying the optical properties of surfaces can be done by additive or subtractive manufacturing. The only difference is that we remove material from a flat surface, or we add some material to make a patterned surface, and so give the surface a certain optical properties. Different optical properties that can be tune are the reflection, the diffusion properties, the diffraction. So there are several optical properties that can be tailored, and we have it very controlling on the portfolio, this kind of tailored properties. And the laser texturing can be produced also for the fabrication of very nice optical surfaces, and but also for medical application or for other applications like microfluidics, friction reduction, or wear resistance of heat exchange improvement. So this is the end of my presentation, and I will be glad to answer any question that you may ask from that. Thank you very much for the opportunity.
Thank you, Francisco. Thank you very much. We have time for 1 or 2 questions. I don't see any yet. We have one from Anupam Mukherjee. What kind of polymer substrates you have tried?
We have tried so far PEN, PET, and another one I don't remember, but I think 3-4 different polymers, and the addition was quite good, and the shape and the effect, optical effect, was also very good. Some of them, the roughness was not that good, but for example, as I shown with paper, the paper was a bit rough, but the effect that we could fabricate was still very good.
Okay, thank you. And we have a second question from, again, Anupam. Is there any challenges using polymer or limitation?
The challenges as a substrate.
Yeah, I guess so. It's not precise.
What?
Yes.
Okay, as a substrate. One of the challenge is that is the kind of resist that you want to use, because some of the resists require of an additional step of preheating before the photopolymerization in order to improve the addition. So if the polymer does not withstand this pre-baking process, could be a problem, but only if the addition is not good. If the addition is good, it's still feasible. For example, with the PEN, we did without the pre-baking step, and the addition was very good.
Okay, thank you, Francisco. If you have any questions to ask to Francisco, please keep them for the questions and answers section at the end of this webinar. Thank you, Francisco, again. Let's move on to the next presentation, which is Ronan Batkan from Dublin University. Hello, Ronan.
Hello, everybody.
Please go on.
Okay, let's share my screen now.
Nice landscape.
Okay. Okay, can you see my screen?
Yes, perfect.
There we go. Okay, good afternoon, everybody. So my name is Ronan McCann, and I'm one of the lead researchers on the NewSkin project based out of Dublin City University, and I'll be talking today about laser micro and nano structuring, specifically for ceramics, but this is adaptable to other materials, metals, and polymers as well. Just briefly, so Dublin City University, coming from a lovely sunny day here on the east of Ireland, and our team brings together a lot of expertise across manufacturing technology, and very much specifically looking at laser process development and upscaling of this technology through either Industry 4.0 or digitization, but also we look at the applications of these laser textured surfaces in the either mechanical environments or for the marine as well. And inside NewSkin DCU, we're one of the RTD partners, specifically looking at laser processing, and we are developing a test bed for laser surface nanostructuring and upscaling this technology for industry. And it has a wide range of applications that we can look at. And we're talking specifically about ceramics today, but again, keep in mind this can be adapted for many other materials and processes. So when we talk about laser material processing, if you're not an expert or need a refresher, it's about the direct application of laser light to surfaces, either for surface modification, which could be chemical, or for direct structuring through ablation and melting. And based on the application, there's a lot of different potential applications, from thermal processes such as laser hardening, all the way to micromachining, nanomachining as well. And the choice of the laser is very much driven by the application we're looking at. So as if we look at laser thermal hardening or welding, it's very much a different process space to that of micromachining or nanomachining. So the two processes cannot be done with the same light source, and so to combine two light sources into a single process gives us this multimodal approach that's needed. And in terms of laser ablation as a manufacturing process, it's very adaptable. As you can see on the right-hand side, we can produce structures from micron-sized all the way up to tens of microns or hundreds of microns or millimeters. Or we can extend this even below the single micron to the nanometer scale, which makes it a very competitive technique and fast as well when compared to some techniques for this sort of precision micromachining. The multimodal approach we're looking at developing incorporates a laser heat treatment source, which is a welding laser for surface heat treatment, combined with a femtosecond ultra-fast machining laser. The heat treatment laser allows us to do very precise modification of the microstructure and the surface of substrates and parts. Through the application of this thermal energy, we can have a recrystallization of just the surface to alter the surface microstructure, which leaves a very small process region on the surface while not altering the bulk material itself, which leaves the bulk properties intact while allowing things like surface hardening to take place. With the femtosecond laser machining, we're looking at very high aspect ratio, clean, no burr surfaces for producing these very fine structures and surfaces. And this could be either done through the direct application of the laser light or through what's called laser-induced periodic surface structuring, where very fine ablation takes place and restructuring of the surface due to the polarization of the laser light that's being applied. In terms of the three kind of use cases we've got as an exemplar for this system, we've looked at laser texturing of surfaces and surface coatings, micro and nanostructuring for membranes, ceramics and polymers for the filtration industry, and also bimodal laser processing, combining that laser hardening and surface texturing. But there's, as I said, there's many other potential uses, and if you want to work with NewSkin, we can take a very much work with your materials. We take the approach to develop a process around your needs. And keep in mind that these laser processes developed are compatible with a wide range of both ceramics, but also other materials, including metals and composites as well. The first use case looks at laser texturing of either the materials or coatings as well, and this has a twofold benefit. The first being that we can, through the application of this microscale roughness, reduce the attachment of microorganisms for anti-fouling applications, which is important in the marine, but also to control the wettability, which could be beneficial again for the marine environment, but also for anti-icing in the construction or aerospace sectors. And this gives us not only fine control over the wettability, but also the tribological properties as we define a surface with a defined texture. So this is very applicable to components in any immersed condition, any high friction environment as well, but we can also get surface corrosion benefits through the application of this surface texturing. The unique selling point, of course, is then that these, if a part is in a high friction or a water-facing environment, it has an increased lifetime or reduced cleaning requirements. So what we would look at in terms of the tribological improvements is to produce these dimples or ridges with defined geometrical features and depths. These wells act as both reservoirs for lubricants, but also traps for any parts that shear off from the contact surface. To the definition of dimple diameters, depths, etc., we can get very well-controlled static friction forces and reduction in the overall friction coefficient of the part. We can also get very defined contact angles based on the surface structuring as well, if wettability is a concern for the surface. Another one for anti-fouling looks at very rough surfaces that have very fine micron or 10 micron sizes. And this reduces organism attachment. This shows Ti-6-4 surface that was textured using a variety of different micro-sized surfaces. And overall, depending on the attachment technique examined in the lab, across the board, there was a very high reduction in the fouling of the surface. And some work we've done previously ourselves is the converse of this, is to look at the texturing of polymer surfaces for biomimetic surfaces. And we see that again through the different applications of either rough surface morphologies or well-defined microchannels or dimples, that we can control very accurately the attachment of these microorganisms and in a very precise spatial way as well. And this is a compatible process with other further downstream post-process techniques such as plasma treatment for increased control of the wettability. So it can either be a single step or as part of a multi-stage process. The second use case we're looking at is for ceramic membranes. This would be for the creation of micron or nano-sized pores on any functional material. It could be a ceramic or also a polymer as well. Application areas for these are of course in the environmental and water treatment areas, but also for chemical bioprocessing and chromatography. Or this could be laser texturing of an existing product as well. This is a compatible process with existing materials. And again, the unique selling point here would be for enhanced separation efficiency, to have very fine control over the pore generation on the membrane itself. And again, this gives a longer filter life or better performance, whichever we wish to target. And again, laser processing gives us a very fine control. We can have very fine control hole diameters from the nanometer regime all the way up to microns, and depths, so ranging from single microns up to tens of microns. So we can work with a range of different materials and film thicknesses as well. And this can be done again on coated materials or on base bulk materials as well. Some previous work we've done on this ourselves again has been on high aspect drilling of alumina ceramics for this application, and controlling the laser power, laser process parameters gives us a very well-defined drilling rate, and we can control the density of these pores on the surface as well. And one thing we are looking at inside the NewSkin project is the use, as what Francisco was looking at in his in the previous discussion, was in these use of refractive octagons. And we're using this for the direct application of light to the surfaces for structuring using what's called selective light modulation, where we can control through a reflective LCD panel the number of spots that we're putting down to do simultaneous drilling. This is the added benefit of us being allowed to have defined density of the pore size, but also gives us the ability to upscale the technology and move to high area processing at high speeds as well. And finally, the last use case we're looking at is on laser hardening and surface texturing, and this is for tribological improvement or any friction improvements in parts that are in contact. So this is to combine the laser texturing approaches I described previously with the laser hardening as well, which would be done as a first step. This could be for cavitation reduction or bubble generation on propellers, say, in the water, the marine environment, but also for high wear environments in the energy or mining sector or in the automotive or aerospace. And through the application of this laser hardening process, we can get that microstructure generation where we can have a very hard surface while retaining the bulk properties. This would be done first, and then secondly, we would follow with the laser texturing to get the combined benefit of both of these processes. The fact they're combined into the bimodal process in our system gives us an ability to upscale and increase the processing window size, but also in terms of the speed we're doing the processing at. Again, the unique selling points for this would be for increased part lifetime or friction reduction or wear resistance. Some previous work we've done before shows that through the application of laser thermal hardening, we get very well-defined surfaces that have good wear properties, again, while maintaining that bulk material property. And through varying our process window, we can control the depth of this hardened region on the surface of our part. Depending on what the size of the part are, we can increase this high wear resistance layer for increasing the lifetime of a part that's in contact. It's very important in the automotive and in the mining sector, where we can produce very high depth, high wear resistance surfaces. While if we're working with smaller parts, we can dial this down, control it in a more precise manner to have micron layers, single micron layers of this hardened surface. We can also incorporate the use of process gas with this for, say, nitrogen incorporating for nitriding as well. This can be, again, done as a first step in a process to then incorporate the laser textured on the nitrided surface as well. So in terms of the NewSkin project, as I said, we are an RTD partner. We're looking at the tech transfer of laser processing to industry. And this bimodal laser technique will allow very much a very rapid R&D process if the combined laser thermal hardening and machining is of interest. And we can work, as I said, with ceramics, but also other materials or ceramic coatings. And Ronan will talk later about the open calls that are coming. In terms of our open innovation testbed, so we are looking at the multimodal approach. So we have the heat treatment laser of a 1 kilowatt welding laser. We're combining this with a femtosecond micro and nano machining laser, which has a controllable pulse width. So again, for very high aspect ratio, very high precision micro machining if required, but you can scale this up and reduce the precision while increasing the speed within a certain process window to help optimize the process itself. In terms of our optical setup, we are looking for that laser-induced periodic surface structuring for the nano regime, but also the optical phase modulation to upscale hole drilling and surface machining to allow for rapid, large area processing. And we're coupling this with in-situ metrology, such as pyrometry, thermal measurements, and interferometry, so we can have a look at the surfaces and rapidly optimize what we're producing in situ. In terms of what parts we can handle, we have a 4-axis motion control system that can handle a maximum flat size of about 0.5 meter up to 0.9 of a meter, or a 0.4 meter diameter cylindrical envelope for round samples. And again, the applications, as I said, for nanostructuring and drilling, heat treatment and surface hardening, but we can also go to high aspect ratio piercing and other applications as well. So I suppose just to end with an outlook as to our soon-to-be online laser processing facility. It offers a very rapid, quick, and upscalable route towards the generation of well-defined dimensions on surfaces, on ceramics, and other materials. The laser heat treatment would allow us to combine the advantages of laser thermal hardening and corrosion resistance with femtosecond laser processing for surface structuring, which gives us a very wide range of applications that we can potentially work with. And ultimately, this sort of multimodal approach is a key enabling technology for industry that would allow new functional surfaces and materials and components with increased lifetime and wear resistance in their applications. But through this approach, we're looking at rapid fabrication and large area fabrication as well. So thank you, and I'd like to take any questions, or of course you can contact me after the webinar as well.
Thank you, Ronan. Thanks for this presentation. Any questions for Ronan, please? Oh yes, there is one. Okay, so the first one from Anupam Mukherjee. For wear and corrosion resistance, which is the best process among the three processes?
So for wear resistance, I would say the laser surface texturing and modification through the nanomachining is the best process for that. It allows us to produce those surfaces that have lubricant reservoirs and debris trapping as well. But when combined with the laser thermal hardening, the surface itself is of high wear itself. So these combine into a very beneficial process for wear resistance. For corrosion resistance, we would go for just the laser heat treatment. For corrosion resistance, you don't want high surface areas that act as corrosion sites. So through the laser thermal process, we can increase the wear resistance and encourage certain elemental migration to the surface for high corrosion resistance, but also have a very smooth surface that doesn't have those sites for corrosion to occur.
Okay, thanks. I guess so.
And I think I have another question, that you are saying that for if we do the laser structure, then do we need to another hydrophobic coating to get this wear resistance?
It would depend very much on the material, but generally the laser thermal hardening process, depending on the actual process window we're looking at on the material, we can encourage things like elemental migration to the surface such that we have corrosion resistant surfaces, but it would be very much material dependent.
Okay, thank you.
Thank you.
We have another question from Ronan Donny. Do you have experience with powder metal parts, different materials in one part?
In terms of powder parts, so we do look at additive manufacturing through laser processing through laser powder bed fusion. So we have some experience in that ourselves. And then in multi-materials, we could easily work with that inside our inside the test bed. It's been designed in such a way that depending on the amount of energy required, we should be able to accommodate everything from low energy processing with polymers all the way to high energy processing with metals and ceramics. The limiting factor becomes as the material becomes more difficult to process, the laser process itself becomes slower. But it very much is a first instance. We can begin our testing on this, and then if upscaling is required in future, we can develop the process and even indicate what sort of laser systems and light sources would be the optimal to proceed with.
Okay, we have another question from Claudio Ferraro. Could you give some info on the laser polishing for ceramic substrate? How fast is the process, and could it be scaled up for industrial applications? And then during polishing, is temperature generated?
So did you repeat the last part there, Dylan?
The last part was, is there any temperature generated during polishing?
Okay, so yeah, for the laser polishing, if we're looking at using the microstructuring laser for polishing, there is very low thermal gradients present. It's a very ultra-fast process. The material that's removed is removed instantly with very little conduction from the ablation site. So that would be one potential route. The second would be to use the laser thermal hardening process. This generates large quantities of thermal conduction. The melt zone on the surface is much greater than that of the spot, the laser spot. So in terms of that would be a much faster process and allow, say, much smoother surfaces. In terms of the speed, again, it's material dependent. It depends on the melting temperature of the material. But we have a system such that, which is a capable laser welding system, so it can scale up quite rapidly. It would depend on just what the melting temperature is relative to the processing window we have.
Okay, thanks, Ronan. I don't see any more questions. So thank you again. Thanks for your presentation. And now let's move on to the last presentation from Romain Hérault.
Good afternoon.
Hello, Romain. You can share your screen.
Okay. So can you see my screen now?
Yes, yes, we can.
Great, thank you, Dylan. So I'm Romain Hérault from the cluster Alpha RLH. So the Alpha RLH is a cluster based in Bordeaux and Limoges in France, and we are specialized in the photonics industry. We are a partner of the NewSkin project, and as such, we are in charge of managing and developing the NewSkin platform. And during this presentation, I will be presenting you this platform, and I will also show you how you can use this platform in order to connect with the NewSkin partners and also to participate in the NewSkin project through the open calls. So first, we can have a look on how the platform looks like, and this is the homepage of the platform, which is showing the main features of the platform and how you can use it. So first of all, the platform is the main channel to access to the ecosystem. When we speak about ecosystems, we think about the NewSkin partners and the NewSkin consortiums, but also all other organizations that are interested in the nanotechnologies that we develop in this project. So with the platform, you can get in touch with these actors and you can request more information on some technologies that are developed. And therefore, the NewSkin platform is also a matchmaking area. You can use the platform in order to meet and find a partner for a specific project. Indeed, there are some different features that I will present later that will allow you to use some filters and to find specific partners depending on industry needs, projects that they developed earlier, and this will be very useful for participating in new Horizon Europe project, for instance. And the platform is also the main tool for the NewSkin project to offer services and to give access to these services. So we have three types of services in the NewSkin project. The first service is access to upscaling facilities. So during this webinar, we have presented some upscaling facilities such as lasers or high beams, and you will be able to use and cooperate with partners that participated in this webinar to integrate their technologies. You are also you will also able to access to the testing facilities of the NewSkin project. So if your organization is developing a new nano coatings or is using laser technologies to nanostructure specific surface, you will be able to test to use the testing facilities to validate your prototypes. And the NewSkin partners are also planning to offer route-to-market services offered by the clusters of this European project. So among the clusters, you have Alpha RLH and the Pôle Européen de la Céramique, for instance. And then the platform is also a marketplace for your organizations, as your organization will be able to register on the platform and to provide some information on your entity. You will be able to sell products and services through the platform, so you can highlight your services on the platform and sell it internally. So it will be a large database of products and services related with nanotechnologies. In the platform, we are also intending to present all the use cases that will be done, that have been done in the framework of the NewSkin project. So we have described in the previous presentation some of these use cases, and this will be also available here on this platform. And finally, the platform will be the main channel to access to the open calls and to participate in the open calls in order to have a chance to get the free services that would cost up to 60,000 euros. And I will describe this open course later in this presentation. Now in the first part, I'm going to show you how you can get more information on the technology development of each partner. In the NewSkin platform, we have a repository in which we are publishing value propositions. So most of the information you found in this webinar is already available on the repository of the NewSkin platform. So in this value proposition page, you will be able to have a description of upscaling and testing facilities. You will have also more information on each of the partners' competencies that are developing these facilities. Indeed, in the value propositions, you have some short descriptions of the laboratories that are working in the NewSkin project, and how you have more information on the references and projects they developed earlier in the same topic. And you have as well a use case description. So on the value propositions page, you can see here how it looks like. You have on the left side some filters that you can use. So for instance, if you're only looking for value propositions related with the ceramics industry, you can you can just select the ceramics in the industries and use filter and click on filter, and then you will only see the value propositions related with the ceramics industry. You have all the other filters and industries such as key interests and upscaling or testing facilities. So if you are looking for specific testing facilities, for instance, you would like to test a specific surface in icing conditions, you can use the filter to find these testing facilities quicker. And then once you find one value proposition, you have a short description of the entity and of the technologies that will be described in the value proposition. And you can download here in the bottom the value proposition as a PDF, and you can then study this PDF to analyze to what extent you can cooperate with one of the partner and use one of the NewSkin facility. And on the right side, you have a contact items that you can use to contact directly the partner on the NewSkin platform. So the NewSkin partner will receive an email showing that indicating that you sent him an email through this platform. So it can also be easier for you to contact an organization and a specific person who's in charge of developing the value proposition and the technologies. So here you have some example on what you can find in the PDF available in the value propositions on the platform. So you have on the right side, for instance, the upscaling facilities of Alphanov. Alphanov is an RTO based in Bordeaux, specialized in laser technologies, and they are using their femtosecond laser in order to texture metal foils in the framework of the NewSkin project to obtain certain effects such as anti-icing, anti-fouling effects, and they are developing roll-to-roll technologies allowing to texture larger surfaces of metal foils, and you'll be able to use their facilities for your own industry. And you can find their value propositions on the platform. And on the left side, you can see an example as well of what you can find on the platform. This is a picture of the value propositions from the University of Uppsala. So we already presented you the value proposition of the University of Uppsala in this webinar. So I'm not going to go in much details, but this is just an example of what you can find, and you can also find scientific articles on their value propositions if you want to go in more details in their technologies. And finally, on all of the value propositions, all partners, all RTOs are required to send to provide tables and graphs that make it easier for external organizations to understand what are the applications of specific technologies and on which substrate and on which markets these technologies can be used. So this is a table from LITAT, which is an RTO of the NewSkin project, who is specialized in development of nano coatings. And for instance, you can see the applications of their nano coatings on the left side, and if you are looking, for instance, for abrasion resistant coatings, you know that you can see that here that the LITAT is developing one specifically for the metals and ceramics industries, and for these three markets, so pavement, turbines, and engines. So this is just a table to make it easier to understand how we can use the technologies of each partner. And this will be very much important for you to know how you can also use the open calls and the services of the NewSkin projects. So now we are going to see how you can use it, apart from getting some information on the value proposition. On the NewSkin platform, there are several tools that allows you to access to the ecosystems and to network with the NewSkin partners and also other organizations that are interested in the nanotechnologies developed by the NewSkin partners. So here you have a picture of the directory. On the directory, you have a list of all registered organizations in this platform. Here you can find 4 partners that are NewSkin project partners, but you can also, if you do some other research, you will also find organizations that are not NewSkin partners. And you can use filters to find specific partners by industry, technologies, or application. On the NewSkin platform, you have also as well a news section here, and in the news section, it's not only for NewSkin project partners that are able to publish news. Any type of organizations would be able to publish news on this platform to promote a specific product related with the nanotechnologies, or to promote an event that your organization is organizing. And then I will, as a manager of the platform, I will have to validate your news, but basically it's very easy to use, and it's a very good tool to target these specific organizations that are interested in nanotechnologies and in the NewSkin project. And you can also use the news sections to communicate on scientific articles that have been published as well. And finally, in order to offer networking opportunities, we developed a mapping tool that you can use that allows you to find a specific partner easier, to launch a new project, or to use a specific NewSkin service. So this is as well part of the platform, and if your organization register on the platform, you will also appear here, and this will increase the visibility of your activities and your technologies. And this will also be an opportunity to launch new European projects. On these mapping tools, you can also find specific partners by type of organizations, industries, or countries. And now I'm going to give a few words on the open calls of the NewSkin project. So as we said earlier, the NewSkin project intends to transfer its technologies to organizations that are interested in using these technologies. So we will launch 4 open calls from 2022 to 2024. These winners of the open calls will be able to get a free access to upscaling and testing facilities, and the services, like you will be able to get the services that would cost up to 60,000 euros. So this will allow you to test a prototype or to produce a prototype, and we expect to finance up to 100 projects. You can find some information on the open calls on the NewSkin platform, and the NewSkin platform will also be the main portal to participate in the open calls. On the open calls page here, you will be able to find later guideline for applicants, and as well there will be a page organized for you to apply for the open calls, and you will also able to find the exact list of services. So this open call space is in process at the moment, so you can for the moment find some basic informations such as the calendar, how you can apply, and what type of organizations are able to apply. Here on the calendar, you can see that the first open call will be launched on the 1st of October 2021. And then you will have 3 months to apply until the 31st of December 2021. And the selected proposal then will start their project on the 1st of April 2022 in a partnership with some of the NewSkin partners that you have selected. For instance, if your organizations would like to test a specific prototype, you will select one of the testing sites of the NewSkin project, and you will develop your project with a specific NewSkin partner that you have selected. So you can find these information at the moment on the platform, and in order to be able to participate in the open calls and to register on the platform, you will have to sign in on the platform. And I will explain you now how this is going to work. So in order to participate in the bot calls, but also to get in touch with NewSkin partners, you must sign in. So here you have the sign in items. You just need to click on it, and you will have to create your user account. And once you have created your user account, you will still have to add your organization. So if you are working at a university, for instance, and in a specific laboratory, then once you are signing, you need to go in your account and add your organization, and then you can fill in some information about your laboratory or universities or about your companies as it is indicated here. And you will have like a short description of what you are doing first. It's just an introduction. Then you will be able to select some tags such as targeted industries here, as you can see here. You will have as well a list of key interests that you can select, and you will also able to select some of the upscaling facilities and testing facilities you are interested in. This will make it easier as well for NewSkin project partners to identify you and get in touch with you. And once you have created your account, you will be able to use all the features of the NewSkin platform, which are, for instance, contact NewSkin partners or publish some news and candidate for the open calls. Then once we will create the international association, you will also be able to access services of these associations through the platform. But these services will be charged services. So for the moment, we encourage you to connect on the platform, create your account, and follow the activities of the NewSkin project to be ready for the open calls that will be launched from October 2021. So that's the conclusion of my presentation. Thank you very much. And if you have some questions on the platform, I'll be happy to answer them.
Thank you, Roman. Thank you very much. We have one question already from Claudio Ferraro. Article open only to European companies or Swiss, for example, could apply for as well?
At the moment, only European companies can apply to the open calls. But, well, for now, this is what we decided so far, but we still need to work as well on the guideline for applicants. So this might we can discuss whether Swiss companies can apply for the protocol, but at the moment only European companies can apply.
Okay, thank you. I don't see any more. Oh, see, yes. Is it only limited for European base?
Yeah. So as I said, it's for the moment it's only limited to European-based, so companies. As I said, but we are still working on the criteria. So if there are some requests from many organizations, we could find a way to select some of the third countries to participate on the open calls. But for the moment, it's only European based.
Okay, so that's answering the next questions because it was how about Asian-based companies? So
no, not for Russian-based Asian-based companies, not for them. No.
All right. No more questions for Roman concerning the open calls, the platform. I don't see any. Okay, so thank you, Roman. Thanks for the presentation. We will move on the last section, which is just questions and answer section. So during the webinar, we had some questions that we didn't answer to. There were several questions for Thomas. Thomas, I hope you're still here.
Yes.
Okay, perfect. So the first one was from Renard Donny, and the question was, is there a limitation regarding the flatness and the roughness of the surface? Maybe a gear.
I am not sure if I'm not sure what in what way limitation of on the surface roughness, or I'm wondering if it's roughness of the surface to be coated, or how rough the surface gets after the coating.
Maybe Renard Donny, if you're still here, maybe you can precise your question.
Can you hear me?
Yes.
Yes, we can.
Yes, okay. My question is regarding the rough part. Is there a limitation of the part of the roughness of the surface or of the flatness? Do you have problems with the surface of a gear, of a teeth of a gear?
Yeah. Okay. Yes. Now I understand. Thanks. So yeah, the trouble is that here, when I was talking about coatings, then it's typically, well, let's say below 2 nanometers. So if the tools or part surface is very rough, then the coating will not survive because there will be too high local stresses. And I know that gears, that's something that's fairly difficult because as far as I know, they are manufactured fairly rough, and then there is some running in period in which the surface would get smoother. So it's difficult to use such coatings there, I'm afraid.
Okay, thanks, I understand. Thank you.
Thank you, Thomas. We have another question for you from Mohamed Boudifa. The negative residual stress is systematic in I-beams. Why it's positive in the classical sputtering?
Well, okay. No, it depends. But so I mean, typically in sputtered films, one would find compressive stresses. So what I wanted to show in that example was rather that the high beams in high beams, it's easier to control the level of stresses. So yeah, my message would rather be that the stresses can be adjusted in high pins.
Okay, and then could it be measured in this case?
And then, of course, measuring stresses, yeah, it depends. I mean, typically we would use a witness piece like a thin silicon wafer that mechanically bends or buckles, and then it's possible to measure deformation of this thin substrate. So otherwise, measuring strains or stresses is not straightforward. But it can be measured, for instance, this way with a witness piece.
Okay, thank you. Any more questions for speakers? I don't see any. No more questions? Okay, so I think we can end this webinar. Thank you all for joining. Thank you to the speakers. Everyone will receive a survey with some questions regarding this webinar. And of course, as a reminder, don't forget to go on the NewSkin platform if you are interested, and create an account if you wish to be updated on the following events that the NewSkin project will organize. So thank you everyone again. Have a good rest of your day, and see you for the next events. Bye bye.